Welcome to this video, and we are gonna be answering this question. The question reads: the dimensions of a rectangular block of wood were found to be 100, 120, and 200 millimeters with a possible error. So with a possible error of 5 millimeters in each of the measurements, find the approximate greatest error in the surface area of the block and the percentage error in the area caused by the errors in the individual measurements. Well, this might sound complicated, but then it's something that is very straightforward to work around. So first of all, the first part is telling us to calculate the greatest error in the surface area. So now the surface area of a rectangular block. So surface area of a rectangular block with dimensions. So dimensions, that is x, y, and z. As you can see, we have three dimensions here. We have the 100, the 120, and the 200. So meaning we have the x, y, and z. The surface area for such is given by x comma y comma z. Here we're saying is going to be equal to 2, then xy. So you multiply xy, then plus you add multiply yz, then you multiply the xz like this, then the 2 outside there. So this here is how the surface area of a rectangular block with such dimensions is what is given. So now, in order to find the, or in order to approximate the greatest error, so they're telling us to approximate the greatest error in the surface area, So what we do is we use the total differential ds, and so this total differential ds is what is going to help us to calculate or to approximate this greatest error. So we just use the same ds, but ds is defined by the partial of s with respect to x, then that is dx, then partial of s with respect to y, that is dy, then partial of s with respect to z, so that they are being dz. Okay, so this is what I'm going to use. So meaning I need to find this partial of x with respect to what? These partials must be found first of all. So to find these partials, I say partial of s respect to x is going to be, so I look at my my surface area function there, which I'm using, which is here on top. Then I just differentiate that, treating all other variables that is not x to be constants. So what do I get? So I differentiate here what is x in the first part. So look, your 2 you still be outside there. Differentiate what you there, the x, you remain with y. Differentiate what is x, that is you remain with what? With a z there. So this is the partial of s respect to x. Then you go also partial of s with respect to y. This here, what is it going to be? So I look at where my y is. Here I differentiate this, I remain with the x. Differentiate that, I remain with the what? With a z. Then I do also partial of s with respect to what? To z. And this is going to be 2. Then z, here differentiate you, I get what? I get y. I differentiate you there, I get what? I get x. So that's just x plus what? Plus y is what I remain with. So this is what I remain with. These are my partials. Then next, now the dimensions that I am working with, or the dimensions that have been given. Dimensions have been given. They say the dimension. So the first one uh, is what is 100. So meaning x is what is 100. Then you go y. They're saying 120. Then z is going to be 200. So these here are the dimensions. Of course, they're in millimeters. I will not indicate that, but they're in millimeters. Then they are telling me also that the possible error, so the possible error, the maximum error in each of the measurements, which is the possible error in this case, is what is 5 millimeters. So what we're saying is this partial in every one of them, since so meaning it means that this is the same for all of them. So taking modulus of this dy and dy dz, we see that this, they're telling us it's what, it's 5. So they're telling us that it's 5 millimeters. So it's 5 millimeters. That's what they're telling us here now. So why did I put the modulus there? So the greatest approximation of the error is going to happen when is going to occur when each and every WASIS contributes positively to the total change. When each of these changes are going to contribute positively towards what, towards the total change, and that happens when what, when all these dx, dy, and dz is just equal to what, is equal to 5, the positive 5. So they'll contribute when that is like that. So what do we then do next? Next is we're going to plug and chug into what we have here. So this here is what we're going to plug. Since we have this, we have the change, and for every one of these we have, so we can now plug in there. So I rub these. So what do I get next? So this then means I'm going to have ds is going to be equal to 2. For the first one, I have 2. What is my y? My y is 120, so I put my 120 there since y here, plus z. My z is just 200. Then I say plus 2 here. Then x, my x is 100, so 100, plus then my z is just 200, so 200 there. Okay, then from here plus again 2, then I see my x is 100 and my y is just 120, so I'm adding all this. So this here is the greatest, what is going to be, give me the greatest, what, the greatest approximate error. So then when I add the 2 there, I get 2. I add those 2 there, I just get, this will be 320, plus add the 2, I get a 300 there. Then plus 2, add there, I get, this is going to be 220. Okay, then I was forgetting my 5s there, so I have to multiply each and every one of these by the 5. Anyway, let's go back. Let's go back. So we erase this here. Okay, so my 5, I multiply by the 5 there, so this here multiplied by the 5. I go to, then I replace what I had before, that's 100, plus the 200. This here is multiplied by what, 5. Then 2, then going also 100, plus the 120, then this here multiplied by 5. Okay, so my change, my total change, or we're saying now we're using this, or this is the greatest approximate, what error is going to be 2. Then this will be 320 multiplied by the 5, then plus you have 2 multiplied by the 300, 5, plus 2 multiplied by, I add the 2 there, I get 220, then I multiply that by the 5. So this is what I, so this is what I, so ds is going to be, now I multiply all this here, so you see in just multiplication here, you get 300 and like that, then plus you get 3000 for the next one, then plus you get 200 and 2200 for the next one. You add these all, everything, add everything together, you're gonna get 8000 and what, and 40 millimeters. So this here is going to be, or is the greatest approximate error in the what, in the surface, what, in the surface area. Greatest approximate error in the surface area, of course squared like this, because you're dealing with what, you're dealing with the area. So I found the first part, we managed to find the first part, then they're telling us the second part is and we need to find the percentage error in the area caused by the errors in the individual what, in the individual measurements. So how are we going to do this? So we'll keep this, we'll come back to it later. So now here we have to find the initial surface area. What was the initial surface area? So from our formula for the surface area, you have 2 there, then you're going to replace the what, the values here. So you're multiplying, so it's xy, so the 100 multiplied by the y is 120 like this, then I add, then you have 120 multiplied, since it is then x I mean YZ, the 120 multiplied by 200, plus then the next one that is going to follow here is the 100 multiplied by the 200, since it is XZ, like this. So the initial surface area is going to be, so I have two, I multiply this first part, I get 12,000. So you get 12,000 here, so 12,000 like that. Then you add the next one, you get 24,000 here, then plus that one is going to be 20,000. I add everything, then multiply by the 2. I just get, I have 112,000. So this is millimeter squared. So this here is the initial surface area. This here is my initial surface area. But then how do I find the percentage, what the percentage error? So I rub here. So okay, so I find the percentage error. So I said the percentage percentage error is going to be, this here is the greatest error. So greatest error divided by the what, the original or the initial what, the initial area. The greatest error multiplied by the, or divided by the original area, then of course this multiplied by the 100%. So I have everything. I just found this here, the original error or the initial one, then I have the greatest error there. So just replace in there. Okay, so I'm going to have that this here is just going to be, when I put there, so I get 8 like that. Then I have 112,000 multiplied by 100%. Then this is going to be 0.075 multiplied by 100%, and this just gives me that the percentage error is going to be caused by the individual measurements here is going to be 7.5%, like that. So this is how I calculate that percentage error. Well, if you're new, remember to subscribe, and I see you in the next one.